So today we begin with rigid body kinetics, and the simplest form of motion of a rigid body would be translation. So, with a particle, we know that we could sum forces and set them equal to the mass times acceleration, a single vector equation which we could break into, for planar motion, two scalar equations, sum of the forces in the x, sum of the forces in the y. But just as in statics, when you move from a particle to a rigid body, you had to add a moment equation. And so the same thing here in dynamics. The sum of the moments is equal to the quantity called the mass moment of inertia times the angular acceleration. And in statics, we could take the moments, sum of the moments about any point, but that's not going to be the case here in dynamics. We have to be particular about where we're summing the moments. And the most logical place to sum moments is about the center of mass of the body. If you do that, you can say that the sum of the moments about that, an axis through that point, is equal to the mass moment of inertia uh, about an axis through that same point g times the angular acceleration. If we pick any other point, which sometimes is a logical thing to do, then we have to add a couple more terms. We have to add the mass times the acceleration times the distance away from that point. In other words, x bar and y bar are the distances from the point that we're taking the moments to the center of mass g. And we can call the terms on the right side the kinetic moments. Don't worry about the signs of those for just now. We're going to draw those on what we call a kinetic diagram in just a moment. A kinetic sketch or kinetic diagram is drawn in addition to a free body diagram, and again, especially when we're looking at what the signs of the moments are going to be, that can be very helpful in writing the equations of motion. So when you draw a kinetic sketch, you should show the mass moment of inertia times the angular acceleration, as well as the kind of equivalent forces, a mass times acceleration, in the x direction and in the y direction, and we want to show those with arrows acting through the center of mass g. Now, as I said, we're going to start with translation, which means that the angular acceleration is going to be equal to 0. So our equations of motion still have the sum of the forces x, sum of the forces y equal to the mass times accelerations. But now we can either sum moments about the center of mass, set them equal to 0, or sum them about any other point. But we still have these kinetic moments to worry about. So let's look at a typical example. We've got this cart. We're going to push on it with a force F, and we want to know what the acceleration of the cart is. Well, that's just the same as if we treat this as a particle. But if I want to know what the weight distribution is between the front and the rear wheels, now I have to treat it as a rigid body problem. So we can start out by drawing a free body diagram with the weight shown acting through the center of mass G, the normal forces on the front and the rear wheels, and the applied force F. Now when we draw our kinetic sketch, again, we don't have any rotation here, so we don't have to show I times alpha. All we have to show are the mass times the acceleration, those two components acting through g. Now, I show them both here, even though in this case the acceleration in the y direction, of course, is equal to 0. We only have motion in the x direction. So we sum forces, and when we go to sum the moments, well, again, if we look at the sum of the moments about the center of mass, we can set them equal to 0, because the only non-zero force you see, equivalent force you see on the kinetic sketch, acts through point G. But if we choose to use point A instead, then when we sum moments about A, then what we would set them equal to would be negative y bar times the mass times the acceleration in the x direction. Now the negative sign is because if we pick our normal right-hand convention and say that counterclockwise is positive, then you can see in our kinetic sketch that mass times acceleration times y bar would create a negative moment about point A. So when we write these equations, what would appear on the left side of every equation comes right off of the free body diagram. Everything on the right side of each equation would be associated with the kinetic sketch. And so again, those two working together help you write the equations of motion and to keep your sign convention correct. And again, use the same sign convention for both summing forces and moments from the free body diagram. Use the same sign convention for the right side of the equal sign when you're getting the quantities from the kinetic sketch. So next time we need to move from translation to rotation about an axis, or to general plane motion. And for those problems, we have to be able to calculate the mass moment of inertia. And we'll actually spend the next two classes toward finding mass moment of inertia of different bodies.